Welcome to another exciting video for mathematics for vectors. We're going over CrossProduct now. My name is Nate Nessler and this is for Hyperactive Studios. Now we left off talking about cross products and I showed you kind of what it was a bit, and here's the formula for it. So quite frankly, it's not as bad as it looks. It looks kind of scary right now, but if I have two vectors here, basically I'm just going to cross them. I'll show you what I mean. If I want to do calculation for x here, I do it about x, and I just leave out x, and I do it for y to z and z to y. And that's exactly what we got here. And that's what's going on for our calculation. And then moving forward, if I want to do it for y, for the next part, for the y value here, I'm going to leave out y, and I'm going to calculate it for x times z here for ax times bz or bz, and then bx times az. So these get multiplied together and subtracted from each other. And moving on, we have the z here getting crossed out, and we have ax and by and ay and bx, and of course these get multiplied together crosswise like this. That's why it's called cross product. And then you subtract one from the other. Now you'll notice there's a negative sign here on this one versus the other two are basically positives here. So this whole thing, when this mathematical expression gets computed, gets multiplied times the -1. And that's important. Don't leave that -1 out there. That can get overlooked quite easily. So be very careful of that. The x here does not mean multiply. It actually means cross. So when you see an x like this between two vectors, it's supposed to mean cross product. So be careful of that and not get mixed up with multiply for that. I know it's kind of tricky with dot product and cross product because it both look like multiply, but that is the case. Okay, so let's look at this in practice. So over here, our math area, now we see the vector here, and I've inverted it so that it's going up instead of down, but normally it would not be going that direction. And I'm going to pull up the way it's normally going. Okay, so I have several examples for us. So this was the way it was normally calculated here for our normal. And that's typically what you're calculating is the normal. And you're probably going, well, what on earth is the normal? Well, okay, so a normal is going to be the vector that's coming off of one of these faces, so that when the light hits it, it gets drawn. Otherwise, if the vector for the normal is facing away from the camera, away from the light, then it's not going to be drawn because you're going to see the back side of that face. So, see if I can't show a real quick example. I don't know if Blender will show me or not because I might have double-sided normals on here, which would prevent, of course, having it be displayed. So that would be an issue. But let's see if I can't get it to do what I want it to do anyhow. Alright, so this is going to completely make this model look terrible. FYI, heads up here. So if I take all these polys here, and I come in here to mesh, and I go to normals, and I say recalculate inside, and go out, and yeah, we have double normals. Otherwise, so I should be seeing the inside of this model right now, but because I have double normals, it's not doing it. Let's see if there's any way I can make it not show double normals. There used to be a way to do it on the old one, but not real sure if this one's got it or not, because they moved a lot and they've changed a lot of things in the newer one for the better for the most part. I mean, it's really awesome now, but trying to find sometimes things in the new one where you knew where things were in the older one, but the older one was really disorganized, so this one's much better. Definitely a upgrade, big time, for this whole thing. Yeah, I'm just not seeing it. Okay. Ah, here it is, double-sided. Haha. I knew it. I knew that was egg. Well, unfortunately, doesn't look like it's loving me too much here. Oh well. Well, what you would normally have happen is this thing's going to draw double normals no matter what I do. I tried. What normally happens is that when you have these double normals like this, it makes it where you see inside the mesh instead of outside the mesh. But because it looks like there's double normals all the time on here, I'll flip it outside, but well, that was for the, I guess, the silver, right? Ah, the web was double-sided too. Good grief. Okay. Flip inside. See if I can't show this yet. Nope, not gonna happen. It's not really doing it. Okay. Well, you can see that the chrome changed on the look of it. It looks terrible now compared to what it was. But normally what you would do is you would literally see the inside of the model. So when I'm looking at it from this direction here or whatnot, I would actually see the inside of the model instead of the outside of the model. And that would be because the normals would be facing the wrong way. And then this would fix it. Let's see if I can just say flip normals and see if it... Nah, it's still not going to do it. Alright, it's just not going to do it. I can't show you. Oh well. So there's the normals going back outside, so that that way they're facing the light and the camera, and I'm getting the proper result. Now you see the chrome looks correct and everything, but honestly, I should have been seeing through the model. And in a lot of other programs, you do see through the model. That's quite common and normal. It's abnormal to not see through the model like that if the normal is facing the wrong way. But that's the reason why we have to have normal, because we have to have the vectors coming off of those faces for that model. Now, when I was in here, and you see all these colorized, pieces here, this triangle here is a face, and so just like this little X, Y, Z here is where blue is Z here, Y is green, and X is red, the X would be your normal coming off of here. And I can even set this to normal so you can see it. So now it's Z is coming off of here. And so this axis, this little manipulator is literally following the directions of your UV and normal coming off of here. So this is quite literally the same direction that the normal is coming off of this surface. So you get a good idea exactly what's happening there, and so it's perpendicular to the surface. And that's perfect, because we want that to be that way for the light to hit it and everything properly. And just as you would expect, here you come to the corner, it's going to be a different story here. Well, if I can get the corner, yeah, see? So here you have the corner, and it's going off at an angle now. It's going to focus in around that. You can see how that normal is now coming off of that edge there at that angle, instead of flat, and that makes total sense. So it's following along the way you would want it to be. So that's exactly what we need to do, and that's why we need to do cross product so often, and that's the main reason you use it. But it's used for a lot of things, and also for binormals, and you'll see what I'm talking about later on, even more so when we start doing this stuff. But yeah, if the normals are a really, really important aspect of a model. It really determines, it really manipulates the light, how the light plays across the surface, in particular with the specular and things of that nature. So it makes a big difference. Normal mapping is completely based on it. It's what makes the newer games look amazing, versus your older games like from PS1 and PS2. They didn't look that awesome compared to the newer games, PS3, Xbox 360, etc. They're all using normal maps. That was the big deal when Half-Life 2 came out. It was normal maps, is really awesome, and it's what made the graphics look so good when everybody went nuts over it. Well, that and the gameplay was awesome. A whole bunch of other things were great about it. Tons of things, matter of fact. But I mean, you get the idea. The normal maps are very important. So normals are very important. If I do, let me show you a calculation. So these normals coming off these surfaces are super important, and we use them all the time for that reason. Okay, so if I do the cross product of the normal here, and I just call this M1, so that way I can keep track of it, and we can see what M1 comes out to be, and that is 0, 0, negative 28. And that is, if I cross the two, if I cross these two vectors here, then I get this normal. And check it out, it is 0, 0, negative 28. That's exactly what that vector is. See, this purplish one here? It's 0 on X, it's 0 on Y, and it's negative 28 on Z. And I'll show you. Here, I'll do stylize, axes, here you go. Here's your Z, your Z. And going into negative Z, there it is, negative Z right down there. Here's your X going across here, and here's your Y going across here. This little edge right here is Y. So, 0, 0, negative 28. Okay, cool. So, okay, we see the value. And I'm going to make use of this other one here. And this is our E and F vectors we were using earlier that had such perfect numbers in them. So they had like perfect scalars, not scalars, but perfect magnitudes, values. So it made it easy and pretty to calculate. And so that's what we're getting here. So when we do a cross product on it, we also get pretty values for it also. So that's very nice. And so we're going to use that for doing our manipulations here. So we end up with negative 9, negative 6, 6 for this vector here for our normal. And we just called it N2. And I normalized the vectors to display it properly within this graph here so that they're all unit vectors, normalized vectors, so they all have the same length. And we don't end up with this weird looking graph where we have some longer than others. Okay, which is nice. It keeps everything nice and neat. So I'll do the calculation here just to prove that yes indeedy it is negative 9, negative 6, and 6. And that yes, that calculation I handed to you earlier on the picture there on the GIMP is exactly correct. So remember, we're going to eliminate the x-axis if we're calculating the x-axis, and then we're going to multiply, cross-multiply y with z, right? So E1, which is going to be your y, EY basically, and FZ, or F2, right? Multiplied together. And then we have our FY multiplied times our EZ, right? And then we subtract the two from each other, and we get negative 9. And that's just like our algorithm right here. So here you go. See? A, Y, B. So in this case, EY with FZ, and then, EZ with FY multiplied across. So just like that. And then we're going to come over here and hit the next one, and we're not going to forget about that negative. So that's what that little negative is right there. So after this whole thing is calculated, I'm multiplying it times the negative 1 afterwards. That's important to have that in your algorithms. Alright, so here we have our EX times our FZ, and then we have our X times our EZ, and they're subtracting from each other. We end up with 6. Then we multiply that times negative 1 afterwards for the final result there, and we end up with a negative 6. Alright, and then EX here and times FY, and then we have our FX times our EY. And again, because we're doing it on the Z-axis, so which one are we leaving out? We're leaving out Z, so you don't see any 2's in there at all, right? Here we're leaving out Y, so that we're going to leave out, so you don't see any 1's in there, because that's Y, right? Same thing. So we're going to subtract this from this one here, and we end up with 6. Very cool. and it's not too shabby. So once we get that calculated, you'll notice we have exactly -9, -6, 6. So they're identical between the two here. And that's precisely what we calculated out. Now you can also flip a normal. And I wanted to show you this. So like I was flipping the normals in the software. And this is what I was talking about. I should be able to see on the inside or whatnot on the polygons there. But I wasn't. And that's because the normal was, I was flipping it, but I don't know what was going on. But so this is what was happening when I was flipping that normal. See, same normal, it's just now going up to positive 28 instead of negative 28 on the z-axis. So the way I did that is really simple. Basically, you just take that vector, which is normal here, and multiply it times -1 as a scalar. And so then that -1 gets multiplied times each part, right? So I have -1 times 0, -1 times 0, -1 times -28, and I get positive 28 here. So if you need a refresher on that real quick, if I scroll back up here, 0, 0, -28 is the original one. By multiplying the -1 throughout distributive property, and multiplying a -1 times 0, -1 times 0, -1 times -28, I get positive 28. Because a negative times a negative is a positive. Same thing goes for this one too. If I want to invert my normal here, for this one also, then I multiply -1 throughout that normal, and so -9 becomes positive 9, -6 becomes a positive 6, and positive 6 becomes a -6. So you can see it's an absolute opposite of the original one here. And that's essentially how you do a cross product. Now there's one other thing I can talk about, and you may or may not need to use it. It's totally up to you and your situation. Whatever is going to be more beneficial for performance is always what wins out. If you're going to choose to do something, it should always be based on which one's faster for performance. But alright, so that's how the cross product works. That's really all there is to it. Once you code it in, you really don't have to hardly mess with it again. We're already going to be working with built-in cross products, so you don't even have to code it. But if you ever had to, this is how you do it for the algorithm. Alright, so if absolute value, or I'm sorry, not absolute value, but the magnitude of A cross B, which would be your resultant normal vector here, so basically the magnitude of the normal vector, is equal to the magnitude of vector A times the magnitude of vector B times the sine of theta. So you can get the same result from that, apparently. And if you need to use that algorithm, cool, then there it is. But I think oftentimes you're best off just calculating the magnitude of the normal vector, because that would be faster than calculating the magnitude of A and B, and then also doing the sine of theta, as far as what it would take, cost mathematically speaking. It's going to be more computationally intensive. So that's my 2 cents on the scenario, but hopefully that all makes sense to you. And well, it's pretty much covers it. That's all there is to it. So from here we'll move on to matrices and start going over those, and start going over how we can multiply matrices times vectors, and multiplication order for doing transforms, rotations, and scaling for manipulating our objects, models, and points in object space. So from there we'll get into that mathematics and how we can use that to actually manipulate our models in real time in a game in a lot of different ways here. Alright, with that, that covers vectors, cross products. My name is Nate Nessler, and this is for Hyperactive Studios. Thank you very much.